Okay, it's recording. So like I said, the topic is, this is the topic, linear space or vector space. So introduction, let's start by introducing the variables. So capital V will be our vector space. U, V, and W will be our vectors in vector space V. And K, capital K, will be our vector field. A, B, and C, okay, are scalars in K. Okay. So through this presentation, we will use the following set notation. The first one means that A is an element of A, B are element of A. So the third one, it means that all values of X, for every X in A, and then E, capital E, looking in that direction, X, it means that there exists an element X in A, and then A subset A. Okay, that's A subset A, intervention A, and then A union B. And then the last one is an empty set. So here basically I was explaining what is a subset. You can see that A is contained in B. So this is A is a subset of A. And then here you can see that this is the intersection of A and B. So there are those vectors that are between A and B. Now a vector space. By definition, let V be a non-empty set with two operations. The two operations that we have is vector addition and scalar multiplication. Okay. So you can clearly see this. You are adding two vectors U and V in what? In the vector space V. And here we are doing a scalar multiplication. You can see we are multiplying K by U, and this is an element of a vector space V. Now V is called a vector space over field K if the following axioms hold for any vectors U, V, and W, an element of V. So you can see here I wrote A1, A2, A3, A4. So capital A basically stands for addition. So the first four, they are actually the axioms, the first four axioms. Those axioms involve additions. So you can see here the first one say that if you move the bracket, you still end up with the same answer. It doesn't affect the answer. And the second one, if you add a vector to a zero vector, you end up with that vector. Okay, this is a zero vector here. I've been editing this all the time. There's some little mistake that is there. For example, number 3, what number 3 does? Number 3 is actually talking about additive inverse. So if you add a vector to its additive inverse, you end up with a zero vector. Okay, so the last one, it shows that by moving the vector, now you see we started with U plus V, and then we have V plus U. You are not going to change the answer. You will end up with the same answer. Okay. Now the next ones, this is for multiplication. You multiply, we have added U plus V. If you multiply it by K, you end up with this. And then here is a scalar multiplication. A is a scalar, B is a scalar. A plus B multiplied by U, you end up with that answer. AB. So if you move on number 3, just show you that if you move the bracket, this is not going to affect your answer. You end up with the same answer. So multiplying a vector by 1, you end up with that vector. Okay. So here, therefore, a unit scalar 1, an element of K. Okay. So now, what I have here below, I was actually trying to explain, they say this is a vector space. So I wanted to explain this concept of space. What is a space? So here I was using something that's relevant. Let's say we solve we have an eigenvector, eigenvalue of 5. And then when you solve, substitute back this eigenvalue, we end up with K1 plus K2 equals to 0. So it means that K1 is equals to minus K2. If we let K2 to be equals to minus alpha, then it means that in this space E5, the eigenvalue space, this is an eigenvalue space, we have 5 there. So it's equals to alpha minus alpha. And this, you can take alpha out as a common factor. So alpha multiplied by 1 over minus 1. And here, it will depend where alpha is an element of real numbers. So it means that taking any real number and substitute here, you can see this is a space. Okay, if you substitute here, my alpha is 1, we end up with 1 and minus 1. And if my alpha is 2, now we have 2 and minus 2. So it's not just one fixed value, it's actually a space. So we can see we said eigenvector. So this is still a vector. So this space also is another form of vector space, of another form of a space, okay, of eigenspace. Okay, this is an eigenspace. So I was just explaining the concept of space. And now we go to other examples. These are examples of vector space. So we can have a space of k to the power n. Let k be an arbitrary field. So k is just a field. Arbitrary field, the notation k to the power n is frequently used to denote a set of n tuples of elements in k. Here, k to the power n is a vector space over k using the following operations. So it means that if you are given a problem when you are writing a test, to prove that a space k to the power n is a vector space, what we have to do is to show that the vector addition so that we can add. So you can see this is k to the power n. So k to the power n actually means that you start from k and end at n. K1 involving all those elements from k1 up to kn. So in this case, they're showing that we have a1 up to an, b1 up to an. If you add these two, this means you have done a vector addition. Scalar multiplication can just take one vector and multiply it by kn, by k. So we have k a1, k a2, k up to kan. This is shown here. So this is the first two addition. Then we must also show that there is a zero vector in kn. So here I was just highlighting that how can you get a zero vector. You can see that a1 minus a1 will give you 0. So those values will be 0, 0, 0, 0. So this is a zero vector there. Okay. So they also say that and the negative vector is defined by, this is what I've used, this negative vector, additive vector, to get a 0. Okay. So doing this will have shown that k to the power n is what? Is a vector space, the space k to the power n. So there are examples here also like a polynomial space. Okay, so here I was explaining that to show that actually a polynomial can be interpreted as a vector. Let's say, for instance, I give you f t equals to x squared plus 3x plus 1. So if I write ft as a vector, I'll write it in a column vector. So this is 1, 3, 1. Okay, so you can clearly see this is a vector. So that's how we will represent that. Now, if we have gt is equals to x to the power 2x squared plus 3x plus 4. So to do the vector addition, you can clearly see that you can add these two. This will be 2, 3, and what? And 4. So adding this, you can clearly see you get 3, 9, and 4. So we have done a vector addition, something like that. I'm just trying to highlight this. So you can do a vector addition, and it's a usual operation of addition of polynomials, okay? The way you add polynomials the normal way. You can multiply, you can do scalar multiplication. You can multiply a polynomial by a scalar. It can be any scalar, 2, 3, 4. In PT, it's usually operation of a product of a scalar k multiplied by q in PT. And also there's a way you can subtract two polynomials to get a zero vector. So this means a zero polynomial is also there. Basically, you can see that 0x squared plus 0x is also a polynomial, isn't it? Plus 1, 0 there multiplied by 0. So this will be a zero polynomial there. Okay. Now, this one I'm not going to explain. They just wrote a polynomial in another form. So everything that holds for polynomial will also hold for this one. It's just they wrote in a different form. Now we come to a metric space, M by N matrix. So I was just indicating that M by N can be 3 by 3, it can be 2 by 2, okay? Then the notation, this is important, we'll do another example. The notation M by N of a simple M will be used to denote the set of all M by N matrix with entries in a field K. The M by N is a vector space over K with respect to the usual operation of matrix addition and scalar multiplication of matrices, okay? So let's see if I didn't jump in. The next one is a function space. So function space will relate to polynomial space, okay? So that they are just explaining that, and they are showing you a zero vector and a negative of f is a function minus ft. So these notes will be available to you. You can go through them. And also here they are showing that fields and subfields also, they can be seen to be a vector space. So they say suppose a field E is an extension of a field K. That is, suppose E is a field that contains K as a subfield. Then E may be viewed as a vector space over K using the following operation. So for addition, add two vectors in this extension field E, and its usual addition in E, okay? Then scalar multiplication, K multiplied by U, and so on. So those are two things that we have to do there. Okay, now as mathematicians and engineers, we usually prefer to work with numbers. Now, let's start with linear combinations and spanning set. So linear combination, let V be a vector space over a field K, and a vector V in a vector space V is a linear combination of vectors U1 up to UM if a vector space V, there exists in a vector space V, there exists a scalar A up to AM in K such that this is the case. So it means that for you to prove that something is a linear combination, you have to write it in this form. Whenever I ask you to show that something is a linear combination, let's say for instance we have 1, 2, 3, and what? And I ask you to write this vector is what, V1, as a linear combination of V2. So V2 is 4, 8, 12. So you can clearly see that V1 is equals to V2. V2 is equals to 4
Well, I
V1.
think I'm getting lost here on V1 and V2. The numbers, where did you get the numbers?
No, I'm just explaining using my own creation of numbers. Okay. Okay, let's say again we have let's say 0.1, 0.2, 0.3. So this one we can make, let's say V3. So you can actually write, I wanted something that you can do it mentally without using a calculator, without doing computation. So I can ask you to write V2 as a linear combination of V1 n plus V2. Alpha V2. So what you have to do, you have to determine a scalar, a number that you can multiply V1 with and V2 with and end up with, this one is what? This is V3, this is V2, to end up with V2. So I'll show you how to do that. Let me not confuse you. I'll show you in a formal way. Okay. Because this one might work, it might not work, and it will confuse you. Okay, so but what is important, every time they ask you to do linear combination, that will be the formula that you are going to use. Now, on the next example, they say that suppose we want to express 3, this V as which elements 3, 7, and minus 2 in R3 as a linear combination of U1, U2, and U3. Okay, so I've already solved this problem here. I'll just go to a different space, try to solve it again for you. So we have V is equals to 3, 7 minus 4. So we'll solve it somewhere. If we encounter a problem, we'll come back to this one and check if our solutions correspond. U2 is equals to 2, 3, and 7. You can also copy it. And then U3 is equals to 3, 5, and 6. So let's use the node 1. So here, we want to write V as a linear combination. So it's going to be alpha 1. So this will also be a vector plus alpha 2, U2 plus alpha 3, V3. Okay. Now you are given that not U3, not V, U3. And you are given that U1 is equals to 1, 2, and 3. And okay. Another thing that I wanted to highlight here, U1 was given as 1, 2, and 3. So I write it as a column vector. So I'll be using column vectors to solve it. Okay. And U2 was given as in this form 2, 3, and 7. So I'm going to write it as 2, 3, 7. And similarly, U3 is equals to 3, 5, and 6. So this is what is given to us. And we are also given V. So V, so what we want to prove? We want to prove that 3, 7 minus 4 is equals to alpha 1, 1, 2, 3, plus alpha 2, 2, 3, 7, plus alpha 3, 3, 5, and 7. So this is what we want to show. Now we can write this as an argumented matrix. So in an argumented matrix form, this will look like 1, 2, 3, 2, 3, 7, 3, 5, 7. Okay. Now, I want to see something. Did I copy them correctly? Otherwise, they won't work. So it's 1, 2, 3. No, it's 6. 1, 3, 5, 6. Okay. 3, 5, 6. 3, 5, 6, not 7. Three, 5, 6. Okay, now, so this one will be 6 also. So let's check what we do here. I said we write it as an argumented matrix. So this will be 3, 7 minus 4. Okay, now how do you solve this one? You can use the Gaussian elimination to reduce this to row and echelon form. So we are going to get rid, this must be 0, this guy must be 0, and this guy must be 0. So the first one, R1, you multiply it by minus 2 plus R2, it gives you R2. So this is 1, 2, 3, and 3. So this will be equals to what? 0. You multiply by minus 2 there is minus 4 and 8. This will be minus 1. You multiply it by minus 2 and 8. This minus 6 and 8. This is minus 1. Minus 2 is minus 6 there. Multiplied by 3. Minus 6 and 8. This is 1. Okay. Now for the second one, the operation, you multiply minus 3 R3 plus R1 plus R3 gives you R3. So you do that operation. Minus 3 and 8 is 0. Minus 3 and 8 is 1. Minus 3 and 8 So that will be minus 3. So this minus 3 multiplied by 3 is 9 minus 9, and you add, you end up with minus 3. So minus 3 multiplied by 9, and you add, you end up with what? Minus 13. Okay. Now, on the last step here.
Sorry, sir.
Okay.
I can see in the matrix the first vector, the second vector, and the third vector, and that stroke, and 3, 7, and minus 4. 3, 7, and minus 4. Kana, how did you get that?
It's given. Let's go to the question.
Oh, I see.
It's 3, 7, and minus 4.
Oh.
So we want to show that we can write this as a linear combination of U1, U2, and U3. So you must solve for alpha 1, alpha 2, and alpha 3.
Okay, sir. I see. Sir.
Yeah. Okay, so we're here. So now here we can just add.
So on the R's, how do you know which number you use to eliminate numbers? On the R1 and R2 is equals to R2.
Okay, look here. Let's name them. This is R1. Yeah? This is R2. This is R3. So on R2, you have 2 here. Your lead, this one, the first one, R1, you can see the leading entry is 1. So to make 2, 0, what do you need? The additive inverse. 2 minus 2 is equals to 0. Do you agree with me?
Yes, sir.
Yes, that's what motivated me to do this. So if you multiply the whole of row 2 by minus 2 and add to row 2, then we'll achieve 0 here. Can you see that?
So will that be always the case? Because problems are different.
No. You
so
must
how will we
interpret
know
your
which is
equations. Sometimes you might find that your leading entry here is 0 here. If it's 0, what do? We interchange equations. You look for equation that has got non-zero entry there, and then you substitute there. Or if you are like, you can take the any equation that has got a leading entry to be 1. Okay, you might find that in some situation, all of them, like in the previous class, all of them were not 1. So one of them it was 3, 5, and 3. So if you're in that situation, you can just solve it as it is, or you can divide one equation by, let's say the leading entry is 3 here, you divide by 3. But usually I try to avoid fractions, but sometimes it's impossible to avoid them. We can just, if in that situation, you can use fractions, but it will depend. Okay, so but it's always the case to use the one. In this case, you can see that if we have 1, then it will be always the case. If the leading entry is 1, then you'll use it to get rid of others. Okay, like here I multiplied equation 1 by minus 2 plus equation 2, I end up with 2. Equation 3, 1 multiplied by minus 3, you add to 3, you get that. That's it gives me 6. Okay, now on the next step now.
So, sir.
I'm listening.
Yes, sir. So there's no unique sequence in doing this. Like you can do it the way you want it, depending on the goal you want to achieve, right?
Yeah, depending on the goal you want to achieve. Yeah.
Also, but then there's no unique sequence to it.
There's a sequence. If I'm following a sequence, I start first getting rid of 2, getting rid of 3, and getting rid of 7. That's how I follow. Can you see that? I start getting.
So there's no way that I can start with.
Yeah, that's the you see, I'm moving in this direction. I start here, make this one 0, make this one 0, make this one 0, then I'm done.
But then what if say I start with, what if I take row 3 and then I subtract it with row 1 to get row 3 instead of starting with row 2?
I think if you follow this, it will simplify your life. I think it will still work, isn't it?
Yes, hence I'm asking that there's no unique sequence to this.
But I
can
think
start with 3 and
let's think deep now. Are you not going to need row 2 at some point to get rid of 7? Can you see that you need row 2?
oh yeah, yes.
Yeah, so I think you should follow my sequence.
Yes.
Yeah.
I don't understand.
Yeah?
I didn't understand the point where you said
You said what? I'm listening to your question.
I'm saying, say, I didn't understand when you said we kinda need 7 on row
No,
2.
what I'm saying is this. What I'm trying to explain is that follow this pattern. Get rid of 3, get rid of 2, get rid of 3, and then get rid of 7. Because what I'm saying, if you start with getting rid of -3, how will you get rid of 7? Because if you follow this way, it becomes easy. It helps you actually to get rid of 7, which I'm going to do now.
So, say, after this problem, can you example that contains negatives?
Negative like what?
Let's say it's -2 at row 2.
How the negative sign doesn't matter. You interpret this, you should view this as equations. The method that we are using here is the same method as the elimination method that we used in high school. If you look at it, basically, here we have x plus 2x plus y equals to 3. And here we have 2x plus 3x plus 5. This is z. This will be y. Okay, so let's make this y and this z equals to 7. And this is 3x plus 7y plus 6y equals to -4. Now, in high school, if you're solving this using elimination method, you will say multiply equation 1 by what? By -2 and add to what? To equation 2. It's the same thing. Can you get that?
Oh,
Yeah, it's the same thing that we're using, but it's instead of here, you get rid of variables and focus on the coefficients, but still using that method that we're using in high school of eliminating variable. This means what are you eliminating there? You'll be eliminating x. Can you see that? That's what we use. Yeah. No, I'm trying to
You'll want
relate.
I and Z.
That's what. Yeah, I just want to relate that this is something that we have done before. It's just that we are doing it differently. I hope you can see that. Okay.
So, sir, here we are trying to do an identity matrix.
No. You don't want identity matrix. What you are doing is got a name. You are doing Gaussian. So if you want to need more information, go and check Gaussian elimination. The method is called Gaussian elimination.
No, what I'm saying is that we need to have 1 0 0 0 1 0 and 0 0 1, like here.
Yeah, but it's not called identity because we're not going to solve for everything. We'll use back substitution to solve the remaining values. We only get rid of 2, 3, and 7. After that, we use back substitution to determine the values of alpha 1, alpha 2, and alpha 3. Okay, let me complete it, then we can argue after completing so that you'll be seeing what I've done. Okay, so let's say this is 1, 2, 3, and 3. So here we have 0, -1, -1, and 1. So I said we are doing this operation 2 plus 3. The aim is to get rid of this 1 here. So we end up with 0. This is 0, 0, because 1 minus 1 is 0. -1 and -3, we're adding them. This will be -4. -1 and -13, this will give me -12. So from here, I can conclude that -4 alpha 1 is equals to -12. This implies that alpha is equals to 3. Now I go to, I was solving using the last equation. I go to the second equation. minus alpha 2 minus alpha 3 equals to 1. I substitute, this is alpha 3. I substitute my alpha 3, so minus alpha 2 minus alpha 3 equals to 1. So this implies that minus alpha 2 is equals to, is it 4? Yes. So this means alpha 2 is equals to minus 4. You'll check that one with me. Check that one, is it minus 4? Now you are remaining with alpha 1. Alpha 1 plus 2 alpha 2 plus alpha 3 is equals to 3. You substitute these two. So alpha 1, so if you substitute alpha 2 here, this gives you minus 8. And if you substitute alpha 3, this is 3 here. Alpha 3 here, which is 3, this will be 9. So this is L is 3. So this means your alpha 1 is equals to, so this will be positive 1. So alpha 1 is equals to 2. Okay, now what does that mean? It means that now we can write our given 3, 5, and 6
Sir,
is equals to, hello?
aren't you gonna multiply that -4 with alpha 3?
Yes, you multiply.
That -4 is not -4 times alpha 3.
It's alpha 2. I said this is alpha 2.
Okay.
Is it okay? I was solving for
No.
alpha.
I'm saying that -4 multiplied by alpha 3 equals to -12.
Where?
The first equation.
You are referring here.
No, go up.
Up. Here.
Yeah, there. Yeah. That -4.
I'm dividing by 4, -4 on both sides.
Yes, I'm saying that -4 is not -4 multiplied by alpha 3.
Oh, I see your point. It's alpha 3. Okay, thank you. Yeah, that's correct. Okay, now you have 3, 7 minus 4. So this means you are focusing now. Equals to alpha 1. And my alpha 1 is 1, 2, 3 plus, okay, we can substitute values. Okay, or let me write first. Alpha 2 multiplied by 2, 3, and 7 plus alpha 3 is equals to 3, 5, and 6. So now we substitute these values of alpha. Let's see. The left-hand side must equal to the right-hand side if we have solved it correctly. Okay, now alpha 1 is what? Is 2. So it's 2, 1, 2, 3. And plus alpha 2 is what? Is 2. So this is 2, 3, and 7. And this one must be negative. Where is alpha 3? Is my all of the one of them is negative. Alpha 2.
Sir. 4.
Hello?
Alpha 2. We
It's
got
minus,
alpha 2 is minus 4.
yes, thank you. I see that now. Okay, thank you. So this is 3. And then this is 3, 5, and 6. So now, what remains is to prove that the left-hand side is equal to the right-hand side. So to do that, you can just multiply. This is 2, 4, 6, minus 8, plus minus 8 here, minus 3, minus 7, plus this will be 9, 15, 18. So let's add. So if we add the top ones, what do we end up with? What? We have 11 minus 8. This gives me 3. We have 19. This is 12 here. 19 minus 12 gives me 7. And we have, this is 6. The last one, there's something wrong. I wrote too fast and I made a mistake. This one is minus 28. Minus 28 plus 24, this gives me 4, and this is negative 4. Okay. And can you conclude that the left-hand side is equal to the right-hand side? So we have proven that this is the case. This is 3, 7, negative 4. So this is linear combination. This is how you do the linear combination. So a Gaussian elimination here, it was a tool that helps us to achieve the linear combination. Okay.
So say in conclusion, we must know that using Gaussian elimination, alpha 1 is like X, alpha 2, Y, alpha 3 is Z, just like that.
Yeah, it's the same. You can use X, Y, Z.
Okay.
Yeah, it's your choice, that one. But remember, this is a scalar. Or if you use X, Y, Z, sometimes it looks like they are variables, but it's fine. You can use X, Y, Z. Explain that they let them be scalars so that I don't get confused when I mark your script. Sometimes I get confused and give you wrong when you're supposed to get a correct answer because of your presentation, not necessarily that you are wrong. Okay? So explain it to me so that I can understand. Let X, Y, Z be scalars, and then you solve. Then I will understand everything. Okay? This is a solution. I'm done it here, but it's mixed masala there. I was explaining to students there. And now the next one. They say now, suppose we want to express a polynomial. So you copy that polynomial as a linear combination of P1, P2, and P3. So this one I didn't solve basically with other students in the previous class. The reason I didn't solve is because you'll go through the same steps as the previous one. The only thing that is different here is that that can confuse you is that you must write this polynomial as a column vector. So you can see here the first one. Where is that on P1? I wrote it as 1, 2, 2, and P2 I wrote it as 2, 5, 2, and P3 I wrote it as 1, 3, and 6. So this is, we are actually using column vectors. So once we've written like that, you write it as a argumented matrix, and then from there you use Gaussian elimination. From here you use Gaussian elimination to determine those values of X, Y, Z, or alpha 1, alpha 2, alpha 3, you substitute back. So I end up getting alpha 1 to here is the solution here. Here is the operations that I used. So I end up with alpha 3 equals to 0, alpha 2 equals to minus 3, and alpha 1 equals to 9. I substitute there, and I end up with the original. I end up with V. You can check. So the first one is just 0 actually. So it will just focus on these two. You have minus 6 plus 9, it gives you 3. Minus 15 plus 18, it gives you 3. Minus 24 plus 36. Minus what? Minus the last one there. You should check thoroughly. I can see something might be wrong there. Oh, my consistency is the problem. Yeah, I see what's the problem. So this is 0.
Sir,
I'm listening.
how will we know that? How will we know that the expression is a non-linear combination?
Why do you say non-linear? Come again. I want to explain.
I'm asking that can an expression be non-linear or linear?
Yes, it can. So this is the topic.
So how will you know that?
So the right word that we are supposed to use, non-linear. I don't know. The right word would be.
It's fine.
No, let me explain. Linear dependency and linear independence. I think that's the right word to use. That's still the new topics that we are going to. Yeah.
Oh yeah, I wanted to ask about those.
Yeah, we are still about those two. So this has got nothing to do with linear independence. You still have to cover that too. This is just a linear combination. Okay.
Okay.
Yeah, thank you. So I think the order must be in this fashion. Eh? So we should just check if that was going to give us. So it's going to be 9 minus 6 is 3. 18 minus 15 is 3. 18 minus the last one is what is 4. minus 12. Yeah, it's okay. It's 6. So the way I wrote is the order was wrong. This is correct. But the way I represented them as a linear combination, it was wrong. So this is supposed to be like that. It will give you those values. So you should expect this. This type is good enough. I can give you this type, the same as they are in a major test or class test. He said good level. Okay, now at the next example, express M as a linear combination of matrices A, B, C, where M is equals to that, A is equals to that, and B is equals to that, and C is equals to that. So here, your approach is exactly the same as the previous one, but let's do it. So it's M, I'm just copying it, 4, 7, 7, 9. So we are going to solve it step by step. 1, 1, because it's important. You might get this in future. 1, 2, 3, 4. Double 1, 4, and 5. Okay. The most difficult part is to express, present it. Okay, so this is my M is 4, 7, 7, 9 equals to alpha 1 multiplied by 1, 1, 1, and 1 plus alpha 2 multiplied by 1, 2, 3, and 4 plus alpha 3 multiplied by 1 and 1, 4 and 5. So here we have alpha 1 plus alpha 2 plus alpha 3. We have alpha 1 plus 3 alpha plus 4 alpha. And here is alpha 1 plus 2 alpha 2 plus alpha 3. And we have alpha 1 plus 4 alpha 2 plus 5 alpha 3. So you can clearly see that the first one I just added, this is 10, that 10, and that 10. So it's alpha 1, alpha 2, alpha 3. The next one, it will be this one, alpha 1, 2 alpha 2 plus alpha 3. So that's how I got that one. Now, once you reach this point, it clearly means that we equate. You can see we have 1, 2, 3, 4, 1, 2, 3, 4. So we're equating them. So the first one is alpha 1 plus alpha 2 plus alpha 3 equals to 4. The second one is alpha 1 plus 2 alpha 2 plus alpha 3 equals to 7. Alpha 1 plus 3 alpha 3 plus 4 alpha 3 equals to 7. The last one, alpha 1 plus 4 alpha 2, this is 2 here, plus 5 alpha 3 equals to 9. Okay, now we can write this as an argumented matrix. So this is 1, 1, and 1, 1, 2, and 1, 1, 3, 4, 1, 4, and 5. So this is 4, 7, 7, 9. So again, you'll use a Gaussian elimination to simplify this matrix. Okay, I'm just drinking water. You can try to solve it and come. Okay. Oh, we still have more space here. It's fine. So for this one, I think it will be easy because you can see we have ones. Okay. So I'm going to start with the first one. Row 1 minus plus row 2 gives you row 2. And we do that operation. So this means it's equivalent. It's the equivalent. So the first one we keep it. We don't touch it. So for this one, it will be 0, 1, and 0, and 3. I just use this operation here. It is going to give me that 1 minus 1 is 0. Minus 1 plus 2 is 1. Minus 1 and 1 is 0. Minus 4 and 7 is 3. Now on the second row, the operation is what? Is minus row 2 plus row 1 and minus row 1 plus row 2 or what? Row 3 gives me row 3. So I'm dealing with this one here. So minus 1 and minus 1, 0. Minus 1 plus 3, I think that's 2. Minus 1 plus 3, 4. This will give me 3. Minus 4 and 7, this gives me 3. Okay, and for this one, minus row 1 plus row 4 gives me row 4. So this is 0 here. Minus 1 and 8, this is 3. Minus 1 and 8 here to give me 4. Minus 4 and 8, this is 5. Okay. Now, I want to get rid of these 2. I want it to be negative. And I must get rid of this 3 also. So let's see what we get. Minus row 2 plus row 3. And see what I get. Gives me row 3. So this is the only operation I'm doing. I'll do 2 actually. So this is 1, 1, 1, 4, and we have 0, 1, 0, 3. So if I add, this will be, I multiply by minus 2. So I need minus 2 here. Just for you get 0 and 0. Minus 2 and 8, this remains 3. Minus 6 and 8, this is minus 3 here. Okay. So minus 3 row 2 plus row 4, this gives me row 4. So let's see what I get. Minus, this, the first one will be 0 and 0 here. I'm getting rid of this 3. And then I multiply by minus 3 and 8, it remains 4. Minus 3 and 8, this gives me minus 4. So now I think I'm done. I'm doing back substitution. So these 2 equations, they give me an answer of alpha 3 equals to minus 1. So my alpha 3 is equals to minus 1. And the equation here, it gives me alpha 2 to be equals to 3. And now I'm only left to determine alpha 1. So alpha 1 plus alpha 2 plus alpha 3 equals to 4. Now substituting alpha 1, this will be 3 plus 3 minus 1 equals to 4. So what is my answer there? My answer is that alpha 2 is equals to 2. So now I have...
Sir,
Hmm?
can I ask something there?
Yes.
Go back.
What is the question?
Go up. Go up again. Yeah. Here.
Hmm.
Which equation are we using to get alpha 3? The one 3 is minus 3 or 4 minus 4?
Come again?
Which equation are we using there to get alpha 3?
To get which one? Which 3? Let me show. I'll show you where I think you're asking the question. This one.
Yes, or this the below
Are
one.
you referring to these 3?
Yeah, 3 or 4. Which equation are we using to get alpha 3?
The operation is here. Whenever I'm solving, I give you the operation. This operation here will give you this answer here. And this operation will give you the answer for this one.
No, sir. The one we want to get alpha 3. Until we have to substitute alpha 3 times 3
Can
equals to
I
minus 3.
intervene?
Yeah, intervene, please.
I think he's asking on how to get alpha 3. Whether you use column row 3 or row 4 to get alpha 3. 3 and negative 3 or 4 and negative 4, you'll get the very same answer. Remember, you're gonna have alpha 3 multiplied by 4 divided by negative 4. You'll still get negative 1. And then alpha 3, you're using alpha 3 now because 3 and 4 are on column 3. So whether you use either one of them, you'll get the very same answer. I don't know if you get it.
I get it. What if I don't have the same values? Maybe in row 4 I have 2 instead of 4.
I don't think that will happen.
Please check your row operations. This is correct. The things that lead me to answer, you should focus on these rows. You see these equations that I have here. They are the ones that give me the answers that I wrote there. Okay? These ones, they're important. Actually, when I mark, this is what I'm going to mark. For this question, it's going to be how many marks? 1, 2, 3, 4, 5. And after that, then when I go and look at your equation. So the row operation, they are very important. That's why I'm writing them. You must write them also as you saw. Okay.
That's it. I get his point. Is it possible that we can have different values? Like maybe let's say, if you can see right now, the 2 numbers will give us the same answer for alpha 3. Let's say we have different answers for alpha 3. Which one are you going to consider? And is it possible for that to happen?
No, it's impossible. This means the system will be inconsistent. Then you just write the system is inconsistent.
Okay, cool.
Yes. I hope this answers his question. Maybe we didn't understand it. Okay, now you have alpha 1, alpha 2, and alpha 3. You go and substitute them where? Here. I think we can just do that here. You substitute your alphas here. Alpha 1, alpha 2, and alpha 3. So let's check. Let's use a different color for alphas. So my alpha 2 is 3. So this is 3. And my alpha 3 is minus 1. My alpha 2 is 2. No. It seems like what's going on here? Okay. Minus 1, 3, and 2. Okay, there are 2 values. Which one is which? Oh, this is alpha 1 here. The last one is 2. So this is 2. Now, let's see. We have 2 multiplied by 1 and 3 multiplied by 1 and minus 1 multiplied by 1. So this gives me 5 minus 1, which is 4. So it's correct. So we have 2 multiplied by 1 here is 2. And 3 multiplied by 2 here is 6. Okay. And 1 multiplied by minus 1 multiplied by minus 1 there. Okay, let's see now. I'm going to write it down. It's confusing me. So it's 2 plus 6 minus 1. So this must give me 7. So this is 7. So it's correct. So this one is correct. And then we have 2. I'm writing them down. 2 plus 9 minus 5. Let's see. So this is 11. No. Something is wrong. This is 2 plus 9 minus 4. It's not 5, it's 4. It's my mistake. Minus 4. So this gives me 7. So this 7 is correct. Then we have 2, this 2 here, plus 12 minus 5. Okay, this is 14 minus 5 is 9. So we have managed to write it as a linear combination. Okay, so this is a linear combination. Okay, I hope you understand that. So you can get this type of question. They are at good level. I'm not going to look for others. You can get this ones in a test or major test. So I can just play around with it. Okay, now spinning sets. So if you look at this one, basically, it's related to linear. This is a linear combination. Can you see that? Okay. Now I'll explain this using example. So here they say that show that this set S span R3 and write 2, 4, 5, this vector 8 as a linear combination of vector of S. So somehow this span and linear combination, they are related actually. Okay, let's do this one. I think I copied somewhere. Let's check if I copied correctly. Okay, this is 0, 1, 1, 0, 1, 0, 1, 0, 0.
So what does the R to the power of 3 mean?
It's 3 dimension. Is it okay? My vectors are in 3 dimension. Is it okay?
Okay, sir.
Yeah. So here we are given S is equals to this, my first vector. Can you see that it's in 3 dimension? My second one is 1, 0, 1. And my next vector is 1, 1, 0. Okay. Now I want to write it. So let A, B, and C be an element of R3. Can you see that is 1, 2, 3? Okay. Now I have 0, 1, 1, 1, 0, 1, 1, 1, 0. I have A, B, and C. Okay. So for this problem, my aim, I must have leading entries here, pivots on the diagonal. If I have pivots on the diagonal using a Gaussian elimination, then I can conclude that the given set span R3. So the first thing, I'm going to interchange row 1 and row 2. I want my leading entry to be 1. That's the reason. So it's 1, 1, 0, C. And then I have 1, 0, 1, B. I have the remaining one is what? Is 0, 1, 1, C. Is what? A. This is A. So I have interchanged those rows. So now you know we are using Gaussian elimination. I no longer have to explain that. R1, let's say R2 minus R1. It's nice this way, equals to R2. So this is equivalent to 1, 1, 0, C, and this is 0 based on this operation. Minus 1 and we add to 0, that will be minus 1. We multiply by minus 1 and add to this one, we remain with 1. Minus C plus B, so it's B minus C. Okay, that's the case. Now on the next one, I want to get rid of this one. So, but to avoid confusion, I'll do it in the next step. I'm just copying for now. Now, row 2, let's put it row 3 minus row 2 gives you row 3. And this is equivalent to 1, 1, 0, C, 0 minus 1, 1, B minus C. Okay, let's see. If we add these two, this will be 0, 0, 2. And if we add these two, we have A plus B minus C.
Say,
Yes.
the row operation that you are performing there, you're supposed to add instead of subtract, because you subtract, you're gonna get 2 there. Remember that negative 1 there. Yes.
Yes, now I understand. Yeah, it's correct now. Okay. Okay, that's correct. Now we can see that our leading entry on the diagonal here, we have pivots. So having pivots, it means that we can conclude that S span R3. Then you are done with the first question. Now you need to answer the second one. Okay? You don't have to solve it. You just have to show it ends there. It's consistent and it's going to have unique solution. And then we conclude that S span R3 does it. Okay? Now
before you continue, what are pythons? What are pivot pythons? What did you call it?
Pivot. You see, they are non-zero. Let's just use the layman's language. So these values, they must be non-zero.
On the identity line, on the diagonal.
On the diagonal, yes. Okay, they must be values. They can be 1, they can be 2, they can be 3. Then if you have that situation, then we conclude that S span R3.
Okay, cool. Thanks.
Okay. And now we answer the second question. On the second question, they said we should write 2, 4, 8 as a linear combination of what? Let's go back to the question. Write 2, 4, 8 as a linear combination of vectors of S. Okay. So what I identified today is that I can just to continue from the previous exercise, so that you don't solve again. Last year I was solving again, but I realized that no. I can let my A to be equals to 2, my B to be equals to 4, and my C to be equals to 8. I'll still solve the same system, so I don't have to solve again, do the linear operation again. So substitute in there. I can see that on this row here, I have A plus B minus C, and this will be equals to 2 plus 4 minus 8. This is equals to minus 2.
Sorry, sir.
So
2 and 4 and 8 are just random numbers that you picked, or
no, I didn't pick. They are given.
All right.
4 and 8. So they say write 2, 4, and 8 as a linear combination of vectors of S. Okay. So basically, if you look at it, we talked about the standard basis in the past, né? So you should look at this as a basis. Actually, it's a basis, but it will only be a basis if provided. No. Let me not. This it will confuse me because they are theorems. I must respect those theorems that we have to discuss. So if I talked it out of the blue, I'm not going to respect that theorems. Okay. Now we have proven that this is minus 2. What does that mean? Remember, we are looking for alpha 1, alpha 2. It means that alpha 3 is equals to minus 1. I have solved this equation to determine this guy. Now we go on one on top. We have B minus C. This is equals to 4 minus 8 equals to minus 4. So this means B minus C is 4. So I have minus alpha 2 plus alpha 3 equals to minus 4. I substitute minus 1 here. Minus alpha 2 equals to minus 4. What does that mean? If I transpose this will be minus 3. So this means alpha 2 is equals to 3. So I have solved for alpha 2. Now I'm remaining with the last one. Alpha 1 plus alpha 2 is equals to 8. So substituting alpha 2, I can conclude that my alpha 1 is equals to 5. So now I have solved for this one. Now the only thing that I need to do, I need to write them as a linear combination. So I'm going to do that. So it means that 2, 4, 8 is equals to alpha 1 multiplied by 0, 1, and 1 plus alpha 2 multiplied by 1, 0, 1 plus alpha 3 multiplied by, is it 1, 1, 0? Okay, now let's substitute and see. My alpha 1 is 5, 0, 1, and 1. My alpha 2 is 3, is 1, 0, 1. And the last one, alpha 3 is what? Is it, where is my alpha 3?
Yeah.
Hmm?
I don't understand. Why did you say alpha 1 plus alpha 2 equals to 8? Why didn't you include alpha 3 as well?
Is 0.
Alpha 3 is 0.
Yeah. Based on the equation. Let me explain it again. Where did you end?
Yeah, I can see that.
Let me, yeah, you can see it.
Yes.
We're using this part here. We are doing back substitution.
Okay, I understand now.
Okay. Okay. Now, I'm tired now. We still have 10 minutes. So this is 0, 5, 5 plus 3, 0, 3 plus minus 1, minus 1, 0. So let's add. The first one gives me 2. The second row gives me what? 4. The last one gives me 8. So this means the left hand side is equals to the right hand side. This means our solutions are correct. So we are done.
So now you're confusing me, sir.
Why?
You said alpha 3 is 0, but you're substituting minus 1.
No. Come here. Once we reach this point, we do what we call back substitution.
Yes,
Do you agree with that?
Yes.
Now, look at this equation here, equation 1. That's the one I was using. If I substitute my alpha 3 here, what will be the answer? 0.
Okay.
So,
yeah.
Yes, that's why I said it's 0 there.
Okay.
Makes sense now?
Yes.
Yes. Okay. Okay, I don't have to finish my notes today. I'm not going to be able to anyway. So the next thing that we discuss is what we call a subspace. So a subspace, I'm going to explain it in terms of set theory. So this is a subspace. And this, the big one, is a vector space. So what can we conclude using a layman's knowledge? So a subspace is a subset of what? Of a vector space. It means all the axioms that you have on a vector space, they must be true for a subspace also. It makes sense, no? This is the bigger picture. I just explained what is a subspace. So this is a small set, is contained vector space, subspace is contained in a vector space. So whatever we have discussed at the beginning here, these ones, A1 up to A4, M1 up to M4, this means it must hold. You must look at it this way. If you buy a pizza and you cut a small part, that small part will have all the ingredients of a pizza, isn't it? This makes sense, eh? You have a bigger pizza here, and this pizza is mushroom pizza. So if you cut a small part, the small part will have all the ingredients that were used for the bigger one. Okay, basically that's what I'm trying to explain there. So let's explain. Definition: let V be a vector space over a field K, and let W be a subset of V. Then W is a subspace of V if W itself is a vector space. So it means that a subspace is actually on its own a vector space. That's why I'm saying that it contains all the ingredients of a vector space, okay? All the conditions, okay? Over K with respect to the operation of vector addition and scalar multiplication. Now, to prove that W is a vector space, we need to show that W satisfies the 8 axioms of a vector space. However, if W is a subset of a vector space V, then some of the axioms automatically hold in W because they are already holding in what? They already hold in V. That's exactly what I explained there. Now, this last statement here, it actually simplifies our work. We don't have to prove all the 8. So we'll choose what to show. So you just need these 3. Suppose W is a subset, this is theorem. Suppose W is a subset of vector space V, then W is a subspace of V. It's a subset. If it's a subset, it becomes a subspace. So then W is a subspace of V if the following 2 conditions hold. So we need only to prove 2 conditions. The first one, check if the 0 vector belongs to W. Number 2, prove vector addition and prove scalar multiplication. So if you can prove these 3, then we conclude that the given subspace is what? Is a vector space. So you should be able to prove that. So theorems, they are there to simplify our life. Yeah? So you can even use the theorem without proving it. Okay, this theorem can be proven. Actually, where I copied this, there was a proof of this theorem, but we don't need to prove that theorem. We just need to use this theorem. Okay, like for instance, they say consider the vector space V. This is a vector space, okay? And it's in 3 dimensions. Let U consist of all vector space in R3 whose entries are equal. That is, U is equals to, U consists of A, B, C. It's got 3 elements and those 3 elements are equal. So this set is U, where we can think of U. U is not, it consists of this family of vectors. One of them can be not U1, maybe can be 1 and 1, and U2 maybe can be 2 and 2. So those are equal. Like you see, it's A equals to A, B equals to B, and C, B equals to C. Now here I explain, I said let U equals to A, B, and C, and V equals to what? So this is A1 actually, A1, B1, C1. So I'm just using variable, but you can just use numbers if you want. But explain the concept, the process that you are using. So you can see here A1 minus A1, B1 minus B1, C1 minus C1 will actually give me a 0 vector. Okay, since A1 is equals to B1 is equals to C1. And vector addition, we can add A1 plus A2, B1 plus B2, C1 plus C2. And this actually is still in U, because if I were to use this as an example, we have 1 plus 2, it gives me 3. This is 3, this is 3. So this means U1 plus U2 is still in U. It satisfies the condition of U. Okay, so this is a addition. Now K multiplied by U is equals to So I'm proving this one. This is k multiplied by vector u, and vector u is what? Is 1, a1, b1, c1. So it's k1. So we can write it as k1, k2, k1, k b1, and kc1. So if I were to explain this one here using that concept of, you can multiply vector u by 2, u1, we'll get what? 2 and 2 and 2. And this is still in what? In u. You can see it's here. Okay. So this means now we can conclude that the given u is a subspace of R3. And R3 is what? Is this given as a vector space. So we have actually proven that a subset, this subspace that we are given is a subset U, is actually a subspace of R3. Then you're done. Okay, then there was a question that you asked earlier, linear independency and linear dependency. Okay, so you can just prove one, that the vector is linear independent, or is linear independent. And it fails to meet the condition of linear independency, it actually means that it's the reverse, it's a linear dependent. So let's say I give you 3 vectors and you are proving that they are linear independent, and it failed to meet the requirement of linear independence, then it means that those 3 given vectors, they are linear dependent. Okay, now let's define this. Definition, we say that vector v1 up to vm in a vector space V are linear independent if there exists a scalar a1 up to am in K, not all zeros, such that a1, so if you check in the previous one, we have proven that V is equals to a1 v1 plus a2 v2 plus a2 vn up to vn. But now in this case, they have introduced a zero vector. Okay. So here what they are saying, not all of them zeros. We know that if A1 is 0, A2 is 0, and AM is 0, then it will hold. Everything will be a 0 vector. So the situation that we want is that these guys, they must not have the same value, zeros. One of them must be 2, 3, and 1, and so on. Or all of them, they must not be zeros. Okay, now, linear independence. Now for linear independency, all of them must be zeros. And then I'm done. I don't even have to read this English. For linear independency, A1, A2, and AM, all of them, they must be zeros. If all of them are zeros, then we conclude that the given vector is linear independent. It's linear independent. I hope you understand that. Okay. So now here I'm given, they say that show that vectors 1, 2, this one U, V, and W are linearly dependent. Then after solving, I realized that no man, this vector here is not actually linear dependent, it's linear independent. So I'll negate the given statement that no, they are linearly independent. So I solved. You use so this means you have to master Gaussian elimination. It's very important. So this, I write this according to the definition. According to the definition, I must equate this to a 0 vector. This is the definition that is given. Equate it to a 0 vector. Whatever I've given there, I must solve for A1, A2, and AM and equate it to a 0 vector. That's exactly what I did here. I have 3 vectors. It's 1, 2, 3, 1, 3, 2, 4, 9, 5, equate to a 0 vector, and solve using Gaussian elimination. Okay, we have been doing that. My answers at the end of the day, I end up with, you can see here I have minus 2 alpha 3 equals to 0. What does that mean? It means that minus 2 alpha 3 is equals to 0. You divide both sides by minus 2. So it means that alpha 3 is equals to 0. Then you substitute here. It means that alpha 2 is 0 and alpha 1 is 0. So if all of them are zeros, then we say that U, V, and W are linearly independent because all of them are zeros. Okay, now, I know some students are lazy. For lazy students, you can also use this method, but yeah, you can use this method. 1, 4, 2, 3, 9, 3, 2, 5. You can determine the determinant and prove that it's not equals to 0. If the determinant is not equals to 0, then we conclude that our given vectors are linearly independent. And if it's equals to 0, they are linearly dependent. So this is another method that you can use to show linear dependency and linear independence. Okay, so now because I realized that these vectors are linearly independent, I have given these two, these three. So if you solve these three, the one that I have on top, 1, 2, 3, you will end up with linear dependent. Basically, we have solved this type of questions. You will just write this one as alpha 1 V plus alpha 2 U plus alpha 3 W, and then we equate to a 0 vector and solve. If you solve this one, you must determine a certain value for alpha, let's say 1, a certain value for alpha 2, let's say -3, and a certain value for alpha 3. So this one, I want you to do it on your own. You can copy this one. You must determine this one. And another thing, in most cases in this situation, you'll end up with what? I'm happy because I've done that. When you solve, you'll end up with a row of zeros. You'll end up with 0, 0, 0, 0. What does the rows of zeros mean? It means that we have infinitely many solutions. So in this case, you will let alpha 3 to be equals to t and solve like we did with the eigenvectors. So for this one, you end up with that situation for this one when you solve this one. And then you use this alpha 3 equals to t to solve for alpha 2 and to solve for alpha 2 and alpha 3. Okay. I think I'm going to stop there. In the next class, we can start with example 5, or because we'll have solved this one, we can start with this example. Go and solve this one. You can copy it. Okay, and then we can end our class there. You copy that one, you can take a picture using your phone. So that's where we are going to start. And then in the next class, you can see I'm almost done. What the last 3 pages can take me 45 minutes or 50 minutes. It's not, it will be, then from there we move to transformation of matrix. So immediately after that, we can move to calculus. Okay.
So can I ask?
Yes.
It's I want to ask, when will we write our second major test?
Come again?
When will we write our second major test?
Major test.
Yes, the second one. When are we going to write it?
Major test, I must talk to Majosi. I think it's me who must, I must go and ask for venue.
So?
I think we are going to use the 10th day at school.
I'm not sure if they are.
Yeah, I think we'll use the 10th. That's they have prepared them for exam. Yeah.
We'll write them.
Yeah, we need to book the venue.
All right. So then when do you think we'll write it? Is it somewhere next month?
Yeah, somewhere next month, August.
Then will you give us another assignment?
No. I think at some point the university is going to give us a announcement to come back to university. Once we come back to university, we'll write last test 4 and 5. Last test 5 and 6. It's cool.
5 and 6, are they the only ones left?
Yeah, then we'll be done. We'll write only 2 class tests.
All right.
I think they must come from calculus.
So when are we closing? When are we closing?
I don't know. That one, I think it must come from above. Are you tired?
Yes,
We
yeah,
are
we
tired,
tired.
team. We are tired.
Ah.
Team.
You can't.